In this video, I will talk about the time discretization for advection and diffusion. The solver is IMEX and splitting. And for accuracy, I will discuss about the backward differential equation. This is actually the backward differential formula. So I am Asif Istiak from Andhra National University. I will talk about today about the advection and diffusion. Well, talking here I will talk about the mathematical viewpoint and run the source code from deal2 package, which is 31. This is the one of the output from that source code. So I will try to explain the source codes in some extent and try to modify the source code. So yeah, what is diffusion? Diffusion is the net movement of anything, maybe for example atoms, ions, molecules, energy, generally from a region or higher concentration to the region of lower concentration. And the example of advection is the transport of pollutants or silt or river by bulk water flow downstream. And the commonly advected quality is energy enthalpy. Here the fluid may be any material that contain thermal energy, such as water or air in general. So yeah, for solving this type the advection and diffusion equation here, from that I will tell about the parabolic equation, which can be which is suggested to do the implicit time stepping, and for first order and second order hyperbolic equation, which is explicit time stepping way it has been suggested. And for advection and diffusion cases, the IMEX schemes are can be used for solving that. So this is for the advection, and that can be easily solved by the explicit time stepping. And this is the diffusion. The term states the diffusion where it is suggested for implicit time stepping, and these are the right side. So I can this term I can split this term into the time stepping, which is the k is the range of the time stepping, and u is the current value, whether the u n minus 1 is the previous value. And this term is this term is illustrating the advection property, where here this term is almost the same. You can so here we can say that this is the current value and this is the previous value. So the scheme of the IMEX actually it solved separately the advection, diffusion and source code, and separately, but it can solve parallelly and concurrently by the separate codes. However, if we get we can get the differential values from this one, and after solving these three parts, it will merge into like this type of equation, where this is the summation of the equation, and this part has comes from the advection part, and this has come from the diffusion part, and this is for the source part. However, it can be also illustrated like the delta function, delta form, like this one. So from by solving separately and converging it into the ultimate solution, this IMEX scheme is so yeah, convenient, I think. And actually this one is this one is quite like the Laplace matrix. It is very easy. It is very convenient to use the Laplace matrix where it ranges from h to -1, and for k, the steps of time actually the same number of the mesh size. So the condition number of k times a is equal to a h inverse, and on the other hand the condition number of mass matrix is 1. So in that case we can easily solve it. And also, yeah, for the operating splitting, actually it is available to transport the explicit form, and it can also do the diffusion in an implicit form. And actually one physical effect after other, and it after yeah so it can during solving it can separate the terms. Here you can see it will first solve the advection part, then go to the diffusion part, and go to the source part. So after solving all these, it will give the resultant value like this. So this is called the first order k to the power n, which can be called as Lie splitting, and for higher order the extent splitting can be used. So operator splitting solves mainly the physical problem. So yep, that is another way to solve this type of problems. So what does the Lie splitting actually? The like I will talk it later. Actually Lie splitting solves one full term for one time uh, without associating with other terms. Say for example, if it's solving this advection, it will just for a one step it will just solve the advection. It will not associate with the diffusion, and again if it's solving the diffusion part, then it will not be associated with the advection part. So yeah, for one full step the Lie splitting solve each section separately. And maybe there could be various types of example, like the dust that is roaming around our air, that can be an example in this advection and diffusion, or the reaction, maybe for example hydrogen and oxygen while reacting with each other, it will also diffused. So this is actually the solution variable, where this is the reactant A, reactant B, and reactant C. This is the product with the time, the concentration with the time. So this term depicts the reaction, and this is that for the diffusion. So and also this term can depict the reaction terms. Say for example, this is the first reactance, where this is the coefficient where it is decreasing with the it is showing by the negative form, and UA, which is the first reactant, UP is the second reactant, and this is the second one, and this is the plus, which is being created. So for Lie splitting, I have said that it solves one full step with a one full step. So for the first account for the effect of one step's worth diffusion implicit like that, then it can be solved by the local ODE. Say for example, the a reaction in the combustion engine where gasoline is burned, and there could be various types of equations for diffusion and advection. So it can be also this type of complicated also solved by the ODE. And on the other hand, for strength splitting, it goes for the half diffusion step, then goes to the full one, and then again the half diffusion step, and the order of sub steps can be reversed again and again. So for accuracy, the backward differentiation formula is used because the accuracy is not convenient here, or yeah, the error is quite large here. So for accuracy, the backward differential formula is used. So we have talked about the solvers and the accuracy and the conditions. Now I will show one of the example. Here is one of the example, step 3, which is related about the diffusion with time stepping. So here is the source code, you can see that. So in the source code it will just print out, if I go to the int main section, then for the value of 2 it will give our the flow problem with a time step with the association of the member function. And also let's go to the run section. If I go to the run section, then we can get the conditions. Here you can see the refinement. Well, the mesh number is dependent on the dimension. So if the dimension of this is 2, so if this is 2, then it will print 4, which will depict the 2D, and if it's not 2, then it will print the 3. So this is for the refinement steps, and for initial refinement it will follow this one. And what about the boundary conditions? Here you can see the comment which is convenient for realizing this code also. So this is pretty big, so we can modify the maximal velocity here, or also change the sparsity matrix too. So I have been running this one, and so far it is running up to 541. It will take a lot of time, so let's get to the answer. How the answer would be the answer will be arranged like this manner for 2D, and here you can see for 2D for the refinement. If I go to the run section, for 2D it will give this type of result. And about the 3D, it will give these 3 hedgehog steps, from the fact that the schemes essentially projects the source times of the first time step here.